research, which I just finished up here at the University of Washington. So biologists have studied the relationship between climate and the geographic ranges of species for a long time. For example, this 19th century illustration depicts the geographic ranges of plant species across elevation and suggests that climate plays an important role in determining where we find species. So if you're a plant that hangs out at these elevations, we might conclude that the land above you is too cold, land below is too warm, but right in this area, the climate is suitable. And biologists have used this understanding of the relationship between climate and species ranges to predict that with ongoing warming, the climate that's currently associated with a species range is likely to shift to higher latitudes and elevations, and that in general, species are likely to shift along with it. But of course, climate isn't the only important factor for determining species ranges. Other factors such as soils, disturbance, and interactions with other organisms are also important. So let's examine how we go about making predictions of climate change impacts on species ranges in a little more detail. If we only look at the relationship between climate and species ranges, we'd predict that as the climate shifts, species will shift along with it in line with climate change. But what if there's another important factor at play? Now, this other factor is going to continue to be important as climate change progresses. So as the climate shifts, species are likely to shift their ranges in response, but the influence of these other factors might cause the species to shift in a surprising direction that's not in line with climate change. So if we want to make realistic predictions about the impacts of climate change on species, we need to consider these interactive effects between climate and important non-climatic drivers of species ranges. And so in this talk, I'm going to be looking at the interactive effects of climate and soil on the geographic ranges of plant species. We'll be doing this in the context of Mount Rainier's subalpine and alpine meadows. So as many of you are well aware, the Pacific Northwest mountain meadows have some of the world's most beautiful wildflower displays. They're a major attraction for hikers and nature lovers. They also support a diversity of species, many of which are only found in this habitat type. So let's take a little bit of a closer look at the geographic ranges of these meadows. So as you go up in elevation in these mountains and mountains around the world, the climate gets colder and snowier. And since these are the Western Cascades, when I say snowier, I mean a lot snowier. We get a ton of snow that lasts late into the summer and can severely constrict the length of the growing season for the plants in these environments, as illustrated by the photo here, which was taken in the month of July a few years ago. And along this elevational and climatic gradient, you also see a stratification of the types of plant species you find. So at low elevations, you have dense coniferous forests, which give way to open treeless meadows at higher elevations, and then bare ground and ice at higher elevations still. And with climate change, we'd expect these climatic gradients to shift upwards. And in response, we would predict that trees would start to establish in meadows, often at the expense of the resident meadow species, many of which cannot survive under the canopies of trees. But at the same time, you'd expect meadow plants to colonize bare ground above their current ranges. And so, of course, these seedling establishment patterns would lead to the upward shifts of these meadows. But climate isn't the only environmental factor that's important and varies across elevations. Soil also differs dramatically across the ranges of these meadows. At the lower limit of the meadows, you find very well-developed soil. It's high in organic matter content, has high water holding capacity, high concentrations of key nutrients, and an abundance of soil microbes that can be beneficial for plants, such as mycorrhizal fungi. Above the meadows, however, the soil is a lot different. It's very poorly developed, virtually no organic matter, low concentrations of key nutrients. In other words, on the whole, the soil is not super friendly for plants. And so if we think about climate change, we know these climate gradients are going to shift upwards fairly rapidly. But we shouldn't expect the soil gradients to shift at the same pace, and that's because the process of soil development is a very slow one, happening on the order of hundreds of years, if not longer, at these elevations. So if we're thinking about meadow plants colonizing this bare ground above their current ranges, we might expect this upward expansion of the meadows to be fairly slow because seedling establishment is constrained by poor soil conditions. But if we think about trees establishing in the meadows, they're not going to face these same kind of harsh soil conditions, so their upward advancement into the meadows might be fairly rapid. And if we put those two seedling establishment patterns together, we might expect to see a contraction of the elevational extent of the meadows as they are unable to move upwards as rapidly as they're expanding at their lower limits due to tree encroachment. So that leads to the questions I want to address in this talk. One, what are the interactive effects of climate and soil on seedling establishment? And then two, how might patterns in seedling establishment influence range shifts in this system? So we addressed these questions using a seedling transplant experiment where we planted seedlings into different combinations of climate and soil. So we planted seedlings at 6 different elevations spanning the range of the meadows. And within each elevation, we planted seedlings in a series of plots. And within each plot, seedlings were planted in one of 2 soil types, either bare soil collected from above the upper limit of the meadows, or meadow soil collected from the lower limit of the meadows. And then at each plot, we installed these data loggers, which recorded soil temperatures and allowed us to calculate a variety of microclimate variables related to soil temperature and snow cover duration. And then we came back and we monitored the survival and growth of these seedlings. And I want to emphasize the importance of both of those processes for seedling establishment. Because while the initial survival of seedlings makes establishment possible, these seedlings need to grow to become hardier adult plants in order to have high long-term survival probabilities and ultimately to have the ability to establish. So we modeled both those processes, survival and growth, using a hierarchical Bayesian approach. And I won't go into the details, but when we looked at how to include microclimate into those models, it turned out that incorporating snow disappearance date as the representative climate model or climate variable was the best way to do it. So for the rest of the presentation, when I talk about climate, I'm going to be talking specifically about snow disappearance date, which shouldn't be too surprising if you know these systems and you know how much snow they get and how late into the summer it can last. So we did this study with 7 different focal species. We had 3 alpine herbs, which are all abundant at the upper limit of these meadows, and 3 subalpine herbs, which are all abundant kind of throughout the range of the subalpine meadows here, and then 1 tree species, the subalpine fir, which is the dominant tree at high elevations in the park and responsible for the vast majority of observed tree encroachment into these meadows. Okay, so let's take a look at some results. Starting off looking at the survival of 1-year-old seedlings, so the survival through your first year of life as a seedling. Start off showing the results for just one of the species, the western passflower, very lovely plant. On the vertical axis, we have probability of survival. On the horizontal axis, snow disappearance date. The gray line shows the results for seedlings planted in bare soil, and the brown line shows results for seedlings planted in meadow soil. The shading illustrates the 95% credible intervals. And so what you'll see here is that as snow disappears earlier in the year, survival declines, which was surprising at first because we generally think of snow as being a stressor in this environment because there's so much of it. But as snow disappears earlier in the year, the soil has longer to dry out, and that means that the seedlings are more likely to experience low moisture stress, which these little guys are probably particularly susceptible to because they're first-year seedlings. They have very shallow, poorly developed root systems. Also, we see that soil does not seem to be having much of an effect on survival. So if we look at the rest of the focal species, we see this same general pattern for first-year seedlings. Survival tends to decline with earlier snow disappearance, and soil doesn't seem to have much of an influence. Okay, but what happens after the first year of life for these seedlings? And so I'm going to show some results for subalpine fir, because this is a species that we have the best data for multiple years. And what you see is as you go beyond the first year to look at the probability of survival to years 2 and 3, the effects of snow disappearance date on survival goes away. So there doesn't really seem to be an influence of snow or soil on the survival of these seedlings. So if those environmental factors are impacting seedling establishment, it does not seem to be via survival. So what about growth, that other process? Here you're going to see a different story. So again, I'll start off by showing the results for just one of the focal species, showy sedge. But now on the vertical axis, we have the size of the seedlings at the end of the study as our measure of growth, and again, snow disappearance date on the horizontal axis. And here, for seedlings in meadow soil, as snow disappears earlier in the year, you see this really drastic increase in growth. But for seedlings in bare soil, you see no real discernible effect of snow disappearance date on seedling size. So I think what's going on here is that as snow disappears earlier in the year, you get a longer growing season, and the seedlings have greater potential for growth. But they can only realize this potential if they're in suitably high quality soil, the kind of soil you find in meadows, but not on bare ground. Okay. So let's look at the rest of the focal species. You see the same general pattern in all of the subalpine species, as well as one of the alpine species, the black alpine sedge. But there's two exceptions. Two of the alpine species really don't see an effect of snow disappearance date or soil type on these guys. And these two species are notable because out of all the 7 focal species, you find them in the harshest environments. They are often found in really late-lasting snowbeds, in really cold windswept ridges, in poorly developed soil. In other words, they're really good at tolerating harsh environments. And so they might have evolved a strategy that involves conserving captured resources as opposed to rapidly translating or rapidly allocating those resources to growth. So that's why we might not see much of an effect if we take these species out of their naturally harsh environment and put into more benign climate or soil conditions. Okay, so what does all this mean for range shifts and climate change? I think one conclusion that we can draw is that trees are likely to rapidly establish in meadows. At least that's what the data would suggest, because as snow disappears earlier in the year, which we're expecting with climate change, we see a large increase in the growth of these seedlings. And this will likely translate to higher rates of establishment of trees in meadows and greater encroachment into those meadows. Another conclusion we might draw is that meadow plant colonization of bare ground is likely to be slow, because for meadow species planted to bare soil, we don't really see any positive effect of earlier snow disappearance date on seedling growth or survival, and so there's no reason to expect that they might rapidly colonize bare ground above their current range limits as climate change progresses. And so if we put these two seedling establishment patterns together of only slow colonization of bare ground by meadow plants and rapid colonization of meadows by trees, this would imply that the ranges of the meadows are likely to shift due to this unequal range contraction at their lower limits and range expansion at their upper limits. And this, of course, would pose a serious threat to the species that are dependent on this ecosystem. So on that cheerful note, like to thank all the people and funding sources that made this research possible,